In the shadow of defeat from World War II, Japanese engineers watched in disbelief as America achieved what seemed impossible, sending humans to the moon with computers less powerful than a modern calculator. The Apollo guidance computer, a revolutionary device weighing just 70 pounds with less than 74 kilobytes of memory, was guiding spacecraft 250,000 miles from Earth with precision that stunned even the most accomplished Japanese computer scientists of the 1960s. What Americans celebrated as a triumph of their technological prowess, Japanese engineers saw as both humbling and inspiring, a technological gauntlet thrown down that would forever change how Japan approached computing and precision engineering. Before we dive into this extraordinary story, tell me in the comments, which city are you watching from? It's incredible to see our historical community spread across the world. And if you're new here, subscribe to the channel and turn on notifications. Each subscription helps us continue unearthing these fascinating stories that shaped our world. Now, let's get to the story. The year was 1961, and President John F. Kennedy had just committed America to the seemingly impossible goal of landing humans on the moon before the decade's end. This announcement came just weeks after the Soviet Union had claimed the ultimate Cold War prize by launching cosmonaut Yuri Gagarin into orbit. The space race was no longer simply about scientific achievement. It had become the technological battlefield of the Cold War, with two superpowers fighting for global supremacy through engineering prowess rather than military might. Half a world away, in the laboratories and universities of a rebuilding Japan, engineers and scientists watched with particular interest. Just 16 years after the devastation of World War II, Japan was in the midst of what would later be called its economic miracle. Companies like Sony, Hitachi, and Toshiba were beginning to establish themselves as serious competitors in the global electronics market. But Japan's computer industry remained significantly behind America's, a fact that Japanese technologists were acutely aware of and determined to change. The Apollo program would require solving thousands of unprecedented engineering problems, but perhaps none seemed as insurmountable as the navigation challenge. How could a spacecraft traveling at 25,000 miles per hour be guided with pinpoint accuracy to a specific landing site on the moon, 250,000 miles away? The answer would come in the form of the Apollo Guidance Computer, AGC, a revolutionary device that would have to be invented, tested, and perfected in less than 8 years. At MIT's Instrumentation Laboratory, a team led by Dr. Charles Stark Draper was given this seemingly impossible task. The lab, later renamed the Charles Stark Draper Laboratory, had been working on inertial guidance systems since World War II, but nothing in their experience had prepared them for the challenges of lunar navigation. The computer they would build needed to be extraordinarily reliable, compact, and powerful enough to perform complex calculations in real time, yet light enough to fit within the strict weight limitations of the Apollo spacecraft. When Japanese computer engineers first learned of these requirements, many considered them practically impossible. At that time, computers were enormous, power-hungry machines that filled entire rooms. The IBM 7090 mainframe computer that NASA used for mission planning weighed over 10,000 pounds and required dedicated air conditioning systems just to keep it from overheating. The idea that a computer capable of guiding a spacecraft to the moon could weigh less than 100 pounds seemed like science fiction. Dr. Kazuo Ikeda, then a young engineer at Hitachi's computer division, would later recall in his memoirs, "When we first heard the specifications for the Apollo computer, there was disbelief. We were working with vacuum tubes and early transistor systems that required significant power and cooling. The Americans were proposing to build something that, by our calculations, would need to be at least 20 years ahead of current technology. The challenge was not just the computer's size and weight, but also its reliability. On Earth, when a computer malfunctioned, technicians could simply restart it or replace faulty components. In space, 240,000 miles from home, there would be no such luxury. The Apollo guidance computer would need to operate flawlessly in extreme conditions of temperature, radiation, and vibration. A single error in its calculations could send astronauts veering off into deep space or crashing into the lunar surface. The solution came in the form of integrated circuits, what we now call microchips. Today, they are ubiquitous in everything from smartphones to toasters, but in the early 1960s, they were an experimental technology, barely out of the laboratory. The Apollo program became the world's first major adopter of integrated circuits, purchasing over 60% of all integrated circuits produced in the United States between 1962 and 1967. When NASA and MIT made this decision, it stunned engineers worldwide, particularly in Japan. Hitachi and NEC had been experimenting with integrated circuit technology, but considered it far too unreliable for critical applications. The Americans weren't just using this bleeding-edge technology, they were betting human lives on it. Takeshi Yamamoto, an electronics specialist who would later become a senior executive at Fujitsu, was part of a Japanese technical delegation that visited MIT in 1964. "We expected to see enormous racks of redundant systems," he wrote in a technical journal in 1970. "Instead, they showed us something that could fit in a small suitcase." I remember turning to my colleagues and seeing the same expression of shock on their faces. We knew then that we were witnessing a paradigm shift in computing. What made the AGC truly revolutionary was not just its hardware, but its software. The concept of software as we understand it today was still in its infancy. The Apollo guidance computer's software would need to multitask, a novel concept at the time, allowing astronauts to run multiple programs simultaneously. It would need an interface simple enough for astronauts to use while wearing bulky gloves in the confines of a spacecraft, and it would need to prioritize critical functions like life support and navigation over less essential ones. MIT's programming team, led by Margaret Hamilton, pioneered many concepts that would later become standard in software engineering. Hamilton, one of the few women in a field dominated by men, would later be recognized as a pioneer in software engineering, a term she herself coined. The software she and her team created for the Apollo missions was so groundbreaking that Japanese universities began studying it as soon as information became available. Professor Hiroshi Nakamura of Tokyo University's newly formed computer science department made obtaining information about the AGC's software architecture a priority. "The Americans had solved problems we hadn't even properly formulated yet," he noted in a 1972 academic paper. Their approach to error handling and system reliability represented a completely different philosophy of software design than what we were teaching. As details about the AGC emerged, Japanese engineers were particularly impressed by its user interface. The computer had a simple numeric keypad and a display that could show just a few digits at a time. Astronauts would communicate with it using noun-verb pairs, first entering a code for what they wanted to work with, the noun, then a code for what they wanted to do, the verb. This simple yet powerful interface allowed complex operations to be performed with minimal input, a concept that would later influence Japanese consumer electronics design philosophy. The development of the AGC was not without challenges. As the Apollo program progressed, mission requirements expanded, demanding more from the computer than initially planned. The original memory allocation of 4K words, approximately 64 kilobytes, proved insufficient, leading to numerous programming challenges. Every byte of memory had to be used efficiently, with programmers constantly optimizing code to fit within the tight constraints. This constraint-driven innovation particularly resonated with Japanese engineers, who were beginning to face similar challenges in miniaturizing consumer electronics. Sony's engineers, working on early portable calculators and radio receivers, studied NASA's approach to miniaturization with great interest. The concept of doing more with less would become a cornerstone of Japanese electronics design philosophy in the following decades. By 1966, as the first Apollo guidance computers were being delivered for installation in spacecraft, their reputation had spread throughout the global engineering community. The Japanese Ministry of International Trade and Industry, MITI, which coordinated much of Japan's industrial policy, organized a special committee to study the implications of the AGC for Japan's computer industry. The committee's report, portions of which were declassified in the 1990s, concluded the Apollo guidance computer represents not just a technological achievement, but a different approach to technology development. The Americans have demonstrated that with sufficient resources and coordination, technological leaps that would normally take decades can be achieved in years. This has profound implications for our national technology strategy. As Apollo missions began flying in Earth orbit, Japanese technical observers were stationed at NASA tracking stations in the Pacific to gather as much information as possible about the computer's performance. Every successful mission added to the AGC's mystique among Japanese engineers. When Apollo 8 became the first human-crewed mission to orbit the Moon in December 1968, using the AGC to navigate to and from lunar orbit, it was seen as definitive proof that the Americans had achieved a genuine breakthrough. Dr. Ikeda, who by then had risen to lead Hitachi's aerospace computing division, arranged for a special technical briefing for his team. "This is not just about space exploration," he told them, according to accounts from those present. "This is about a fundamental shift in what we believe computers can do. The Americans have shown that computers can be trusted with the most critical decisions in the most extreme environments, with human lives at stake." The real test came with Apollo 11 in July 1969. As Neil Armstrong and Buzz Aldrin descended toward the lunar surface in the lunar module Eagle, the AGC suddenly began displaying alarm codes. Program alarms 1201 and 1202 indicated that the computer was being overloaded with data from the landing radar. In that critical moment, with the world watching, the AGC demonstrated another revolutionary feature. It prioritized critical functions over less important ones, continuing to navigate while informing the astronauts of the problem. In Mission Control, Guidance Officer Steve Bales, with the help of computer expert Jack Garman, made the crucial decision to continue the landing despite the alarms. They knew the computer was designed to maintain essential functions even when overloaded, a concept called graceful degradation that was revolutionary for its time. When news of this incident reached Japan, it caused a sensation in engineering circles. The computer had not just performed its basic functions, but had managed a complex, unexpected problem during the most critical phase of the mission. Professor Nakamura later wrote, "This was the moment that changed how we thought about computers. The AGC didn't just execute instructions, it made decisions that saved the mission." This shift from computers as calculators to computers as decision-makers would fundamentally alter our approach to system design. In the weeks following the successful Apollo 11 mission, Japanese technical publications were filled with analyses of the AGC and its performance. Electronics manufacturers across Japan began reassessing their research priorities. Companies that had been focusing on making incremental improvements to existing computer architectures now started exploring more radical designs. Perhaps most significantly, Japanese engineers recognized that the AGC represented a new paradigm in the relationship between humans and machines. The computer wasn't simply a tool controlled by the astronauts. It was a partner, handling complex calculations and monitoring systems, while the humans focused on broader mission objectives and decisions requiring human judgment. This human-machine partnership model would deeply influence Japanese robotics and automation philosophy in the coming decades. As Japan began developing industrial robots in the 1970s, engineers explicitly referenced the AGC as an inspiration for systems that could work alongside humans rather than simply replacing them. The impact of the AGC extended beyond technical considerations. For a generation of Japanese engineers who had grown up in the aftermath of World War II, America's technological achievement represented both a challenge and an opportunity. The gap between Japanese and American technology was stark, but the Apollo program demonstrated that such gaps could be closed with sufficient determination and resources. Masaru Ibuka, the co-founder of Sony, reportedly kept a model of the Apollo lunar module on his desk as a reminder of what technology could achieve. "If they can build a computer to take humans to the moon," he would tell his engineers, "we can certainly build one that fits in your pocket." This sentiment would drive Sony's development of increasingly miniaturized electronics, eventually leading to breakthroughs like the Walkman. The technical details of the AGC became required study at Japanese engineering universities. Its architecture, featuring a 16-bit word length, approximately 74 kilobytes of memory, and operating at a clock speed of 2.048 MHz, was modest even by the standards of the late 1960s. But Japanese computer scientists recognized that the true innovation lay in how these limited resources were utilized. Dr. Yoshiro Nakamatsu, the prolific Japanese inventor who would later claim over 3,000 patents, studied the AGC intensively. "What impressed me most," he wrote in his autobiography, "was not the technical specifications, which were actually quite modest, but the engineering philosophy. The Americans had built a computer that did exactly what was needed, nothing more and nothing less." This focused approach to problem-solving would influence many of my later inventions. The AGC's approach to fault tolerance particularly impressed Japanese engineers. Unlike most computers of the era, which would simply fail when encountering an error, the AGC was designed to continue operating even when parts of the system malfunctioned. This was achieved through redundant systems and sophisticated error handling routines that could detect and work around problems. Toshiba's emerging computer division adopted similar principles in their designs for control systems used in Japan's nuclear power plants. These systems needed to maintain operation even when components failed, a requirement that paralleled the challenges faced by the AGC in space. Toshiba engineers explicitly cited the AGC as an influence on their approach to fault-tolerant design. The AGC's memory design also proved influential. The computer used rope memory, a form of read-only memory where programs were literally woven into cores by hand. While this technology would soon be superseded, the concept of permanent, reliable storage that couldn't be accidentally erased influenced Japanese thinking about computer memory. NEC, which would become a leader in memory technologies, studied the AGC's memory systems closely. Their engineers were particularly interested in how the AGC balanced volatile working memory, similar to modern RAM, with permanent program storage. This dual memory approach would become standard in computers worldwide, but Japanese manufacturers were among the first to adopt it for consumer electronics. The AGC's influence extended to seemingly mundane aspects of computer design, such as power management. The computer had to operate on the limited power available in the spacecraft, making energy efficiency crucial. This constraint led to innovative power management techniques that Japanese engineers later applied to portable electronics. Tadashi Sasaki, who led Sharp's calculator development team, noted in company documents that studying the AGC's power management systems influenced their approach to battery-powered devices. The Americans had solved the problem of computing with strictly limited power resources, he wrote. This was exactly the challenge we faced with portable calculators and other battery-powered devices. Perhaps the most profound influence of the AGC on Japanese technology was philosophical rather than technical. The Apollo program demonstrated that setting ambitious, seemingly impossible goals could drive innovation at an unprecedented pace. This moonshot thinking would influence Japanese corporate strategy in the decades that followed. Honda's decision to enter the American automobile market in the 1970s, despite the dominance of domestic manufacturers, was explicitly compared to the Apollo program by company founder Soichiro Honda. "If the Americans can send men to the moon," he reportedly told his executives, "we can certainly build cars that will succeed in their market." Similarly, Canon's ambitious goal of competing with Xerox in the photocopier market, considered virtually impossible in the 1970s, was described as their Apollo project in internal documents. Like the AGC, Canon's engineers would have to overcome seemingly insurmountable technical challenges through innovative thinking and meticulous execution. The AGC's influence was not limited to hardware. Its software architecture, particularly its real-time operating system, influenced a generation of Japanese computer scientists. The AGC's ability to juggle multiple tasks with different priority levels while maintaining precise timing was revolutionary for its era. Yukio Mizuno, who would later lead operating system development at Fujitsu, studied the AGC's software architecture as a graduate student at Kyoto University. "What impressed me most was how they handled concurrency and resource allocation," he recalled in a 2001 interview. "The AGC had to manage multiple processes with different priorities while operating with extremely limited resources." These same principles would later become central to operating system design. As Apollo missions continued through the early 1970s, each successful flight added to the AGC's legendary status. When Apollo 13 suffered an explosion in its service module, the guidance computer in the lunar module, never designed for such a contingency, became crucial to bringing the astronauts home safely. Engineers had to develop emergency procedures that pushed the AGC far beyond its intended parameters. News of how the AGC had helped save the Apollo 13 astronauts further cemented its reputation among Japanese engineers. The computer had not just performed as designed in normal operations, it had proven adaptable enough to be reprogrammed for entirely unforeseen circumstances in the middle of a crisis. This demonstrated a level of flexibility that few believed possible in such a constrained system. The impact of this incident was particularly strong in Japan, where the Apollo 13 mission received extensive media coverage. The Japanese public, already fascinated by space exploration, was captivated by the drama of the crippled spacecraft fighting to return home. For Japanese engineers, the story highlighted the importance of building systems that could be adapted to handle unexpected situations, a principle that would influence Japanese approaches to industrial automation and robotics. Kawasaki Heavy Industries, which was beginning to develop industrial robots in the early 1970s, incorporated lessons from the AGC's performance during Apollo 13 into their design philosophy. Their robots were designed with multiple operating modes and the ability to be reprogrammed quickly to handle different tasks, a flexibility inspired in part by the AGC's performance during the Apollo 13 crisis. As the Apollo program concluded, the AGC's legacy continued to grow. Japanese engineers who had studied its design began applying similar principles to a new generation of computers and electronic devices. The emphasis on reliability, efficiency, and careful integration of hardware and software became hallmarks of Japanese electronic design. Perhaps nowhere was this influence more evident than in the development of Japan's semiconductor industry. Having witnessed the power of integrated circuits in the AGC, Japanese manufacturers invested heavily in semiconductor research and production. Companies like Hitachi, NEC, and Toshiba committed substantial resources to developing and manufacturing integrated circuits, recognizing that this technology would be central to the future of computing. The Japanese government supported this effort through research subsidies and protective policies, seeing semiconductor manufacturing as a strategic industry. This coordinated approach, combining corporate investment with government support, echoed the model that had enabled the rapid development of the AGC. By the mid-1970s, Japanese semiconductor manufacturers were producing memory chips that rivaled American designs in quality and reliability. Their focus on manufacturing excellence and quality control allowed them to achieve remarkably high yield rates, the percentage of manufactured chips that worked correctly, giving them a significant competitive advantage. This focus on manufacturing excellence reflected another lesson learned from the AGC. The MIT team had worked closely with Raytheon, the primary manufacturer of the AGC, to ensure that their complex design could be reliably produced in quantity. Japanese manufacturers took this concept further, developing new approaches to quality control and automated manufacturing that would give them a significant competitive advantage in the global electronics market. The influence of the AGC extended beyond computers to consumer electronics. Japanese manufacturers, having internalized the lesson that sophisticated technology could be packaged in small, user-friendly forms, began developing increasingly compact and powerful electronic devices. Sony's Walkman, introduced in 1979, embodied many principles first demonstrated by the AGC. Like the Apollo computer, the Walkman packed sophisticated technology into a small, portable package with a simple user interface. It was designed to perform a specific function exceptionally well, rather than trying to be a general-purpose device, another echo of the AGC's focused design philosophy. Akio Morita, Sony's co-founder, explicitly connected this approach to what Sony had learned from studying NASA's technology. The Americans showed with their space program that technology didn't have to be big to be powerful, he told reporters at the Walkman's launch. We've applied that same principle to personal entertainment. The AGC's influence also extended to Japan's approach to industrial automation. As Japanese manufacturers began installing industrial robots and automated assembly lines in the 1970s and 1980s, they drew on principles first demonstrated by the AGC for creating reliable, efficient control systems. Toyota's production system, which revolutionized manufacturing worldwide, incorporated computerized control systems that shared many characteristics with the AGC. These systems needed to make real-time decisions, manage multiple processes simultaneously, and operate with high reliability, all challenges that the AGC had addressed in the context of spaceflight. Taiichi Ohno, the architect of Toyota's production system, studied American technology extensively, including NASA's approach to systems integration. While he didn't directly reference the AGC in his writings, engineers who worked with him have noted that NASA's approach to reliable systems influenced his thinking about automation and quality control. By the late 1970s, as Japanese electronics began gaining global market share, American observers started noting the influence of the Apollo program on Japanese technology. A 1978 report by the U.S. Department of Commerce stated, Japanese electronics manufacturers have studied NASA's approach to miniaturization and reliability with remarkable thoroughness. Many of their recent innovations show clear evidence of principles first demonstrated in the Apollo guidance computer. The report particularly highlighted how Japanese companies had adopted and improved upon the concept of designing for manufacture that had been crucial to the AGC's development. This approach, ensuring that products are designed from the outset with manufacturing considerations in mind, had enabled the reliable production of the complex AGC. Japanese manufacturers refined this concept, developing new methodologies for integrating design and production that would give them a significant competitive advantage. As Japan's electronics industry gained global prominence in the 1980s, the lessons learned from studying the AGC became deeply embedded in corporate cultures and engineering practices. The principles of miniaturization, reliability, efficient use of resources, and human-centered design that had characterized the AGC had become defining characteristics of Japanese technology. This transformation was perhaps most evident in Japan's emerging personal computer industry. While American personal computers like the Apple II and IBM PC were designed as general-purpose machines, Japanese manufacturers took a different approach, creating computers optimized for specific uses and user groups. NEC's PC 9800 series which dominated Japan's personal computer market throughout the 1980s, exemplified this philosophy. Like the AGC, the PC-98 was designed with specific use cases in mind rather than as a general-purpose machine. It featured hardware optimized for displaying Japanese characters and was built to extremely high reliability standards, priorities that echoed the focused design approach of the AGC. Tomio Goto, who led the PC-98's development team, had studied the AGC's architecture as a young engineer. "What I took from the Apollo computer was that success comes not from having the most powerful hardware," he explained in a 1990 interview, "but from carefully matching your system to the specific needs of your users." The AGC was designed specifically for lunar navigation, not general computing. Similarly, we designed the PC-98 specifically for Japanese business users, not as a universal machine. The influence of the AGC extended even to the way Japanese companies organized their engineering teams. The development of the AGC had required unprecedented collaboration between hardware and software engineers, who traditionally worked separately. MIT's team had pioneered an integrated approach, with hardware and software designers working together from the earliest stages of the project. Japanese electronics manufacturers, traditionally organized in rigid, departmental structures, began experimenting with more integrated development teams in the 1970s and 1980s. Companies like Sony and Toshiba created cross-functional teams that included both hardware and software engineers working together throughout the product development cycle, an approach that had proven successful in the development of the AGC. This organizational innovation contributed to Japanese companies' ability to bring increasingly sophisticated electronic products to market quickly and efficiently. By breaking down traditional barriers between hardware and software development, they were able to create more tightly integrated systems, a competitive advantage that would help them dominate markets from video recorders to game consoles. The AGC's influence was not limited to consumer electronics. Japanese aerospace companies, studying NASA's approach to reliable computing, applied similar principles to their own projects. Mitsubishi Heavy Industries, working on guidance systems for Japanese satellites and rockets, explicitly referenced the AGC in their design documents for flight computers. Japan's National Space Development Agency, NASDA, now part of JAXA, made studying the AGC a priority for engineers working on Japan's emerging space program. While Japan's space ambitions were more modest than those of the United States and Soviet Union, NASDA was determined to develop indigenous capabilities in areas like satellite technology and space-based remote sensing. Hideo Itokawa, often called the father of Japanese rocketry, arranged for detailed briefings on the AGC for his team. "We must understand not just what the Americans built," he instructed them, but how they thought about the problem. Their approach to integrating systems and managing complexity is what we must learn. This focus on systems integration, understanding how different components work together as a unified whole, would become a defining characteristic of Japanese engineering. Companies like Toyota would later apply similar principles to manufacturing, developing the famous Toyota production system that revolutionized how complex products are made. As Japan's economy boomed in the 1980s, companies that had studied and applied lessons from the AGC found themselves at the forefront of a global technology revolution. Japanese manufacturers dominated markets from semiconductors to consumer electronics, automotive technology to industrial automation. The technological gap that had seemed so vast when engineers first learned of the AGC had not just been closed, but in many areas reversed. American observers began expressing concern about Japan's growing technological prowess. A 1982 report by the U.S. Office of Technology Assessment noted, "In many areas of electronics and computing, Japanese manufacturers have not only caught up with American technology, but have established leadership positions. Their success reflects not just imitation, but significant innovation particularly in manufacturing processes and miniaturization, areas where the influence of their study of American aerospace technology is evident. This technological rivalry would intensify throughout the 1980s, with American policymakers and business leaders increasingly concerned about Japan's growing dominance in key technology sectors. What many failed to recognize was how America's own technological triumph, the Apollo program and the AGC in particular, had helped inspire and guide Japan's rise as a technology power. The story of the AGC's influence on Japanese technology represents a complex transfer of knowledge and inspiration across national boundaries. While the Apollo program had been driven by Cold War competition, its technological legacy transcended geopolitics, inspiring innovation around the world. The computer that had guided Americans to the moon had also helped guide Japan's emergence as a technology superpower. This legacy continues to this day. As modern Japanese engineers develop technologies from autonomous vehicles to humanoid robots, from mobile computing to artificial intelligence, they build on foundations established by generations of engineers who studied and learned from the AGC. The principles of elegant design, efficient use of resources, reliability under extreme conditions, and thoughtful integration of humans and machines that characterize the AGC remain central to Japanese approaches to technology development. In a fitting symbolic connection, when Japan's Hayabusa spacecraft successfully returned samples from the asteroid Itokawa in 2010, the first asteroid sample return mission in history, the guidance computer that controlled its journey carried the legacy of the AGC. Like its American predecessor 4 decades earlier, Hayabusa's computer had to navigate through space with limited resources, operate autonomously when communications with Earth were impossible, and manage complex operations with minimal human intervention. For Japanese engineers who had grown up studying the AGCC, Hayabusa represented a fulfillment of the technological journey that began when they first learned of the remarkable American computer that could guide humans to the moon. The technological torch had been passed, with Japanese engineers now achieving their own moonshots inspired by what they had learned from the AGC. As we celebrate the technological marvels of our modern world, smartphones more powerful than supercomputers of the past, electric vehicles that drive themselves, robots that can perform surgery, we should remember the AGC's role in sparking the innovation that made these wonders possible. The computer that stunned Japanese engineers in the 1960s helped inspire a technological revolution that continues to transform our world. Its legacy lives on not just in the history of space exploration, but in the devices we use every day and the global flow of technological innovation that it helped to catalyze. As Apollo missions continued through the early 1970s, each successful flight added to the AGC's legendary status. When Apollo 13 suffered an explosion in its service module, the guidance computer in the lunar module, never designed for such a contingency, became crucial to bringing the astronauts home safely. Engineers had to develop emergency procedures that pushed the AGC far beyond its intended parameters. News of how the AGC had helped save the Apollo 13 astronauts further cemented its reputation among Japanese engineers. The computer had not just performed as designed in normal operations, it had proven adaptable enough to be reprogrammed for entirely unforeseen circumstances in the middle of a crisis. This demonstrated a level of flexibility that few believed possible in such a constrained system. As a direct response to what they were learning about the AGC, Japanese computer manufacturers began shifting their research priorities. Traditional Japanese corporate culture had favored large, stable, mainframe computers with predictable development cycles. The AGC represented a different approach: rapid innovation, risk-taking, and optimization for specific use cases, rather than general-purpose computing. In 1970, the Japanese government launched what would become known as the Very Large-Scale Integration (VLSI) project, a collaborative research initiative involving Fujitsu, Hitachi, Mitsubishi Electric, NEC, and Toshiba. While officially focused on developing advanced semiconductor technologies, many of the project's leaders had been directly influenced by their study of the AGC. They were determined to not just catch up to American technology, but to surpass it. Hideo Iso, who served as a technical advisor to the VLSI project, had visited MIT's instrumentation laboratory in 1968. What we saw there changed our understanding of what was possible, he later recalled. The Americans had shown that with the right approach, computing power could be dramatically increased while size and power consumption decreased. This became our North Star. The Apollo missions concluded with Apollo 17 in December 1972, but the AGC's influence continued to grow as more details about its design and operation became available to engineers worldwide. When MIT published the complete source code for the AGC in the mid-1970s, it became a treasured resource for computer scientists in Japan and elsewhere. The code revealed programming techniques that were years ahead of their time. The AGC's software was written in assembly language, but incorporated concepts that would later become standard in high-level programming languages. Its error handling routines, memory management, and priority-based execution system influenced a generation of software engineers in Japan and around the world. Japanese computer scientist Ken Sakamura, who would later develop the Tron operating system, credited his study of the AGC as a formative influence. What impressed me most was how they achieved so much with so little, he noted in a 1985 interview. The AGC demonstrated that elegant design and careful optimization could overcome seemingly insurmountable hardware limitations. This lesson shaped my entire approach to operating system design. As Japan's electronics industry gained momentum through the 1970s, the influence of the AGC became increasingly apparent. Japanese engineers who had studied its architecture began applying similar principles to a new generation of computers and consumer electronics. The emphasis on reliability, efficiency, and careful integration of hardware and software became hallmarks of Japanese electronic design. Tadashi Sasaki, the Sharp engineer who helped develop the first handheld calculator, explicitly referenced the AGC in his design notes. If NASA could fit a computer capable of guiding spacecraft to the moon in something the size of a small suitcase, he wrote, surely we could fit a calculator in something that fits in your hand. This thinking led to Sharp's groundbreaking EL-8, one of the first truly portable calculators released in 1970. The EL-8 embodied many principles first demonstrated by the AGC. Like the Apollo computer, it was designed to perform specific functions with minimal power consumption and a simple user interface. While far less complex than the AGC, it represented a similar breakthrough in miniaturization and focused design, packing sophisticated electronic circuits into a package small enough to be truly portable. The calculator's development team had studied NASA's approach to circuit design and power management, adapting techniques developed for spaceflight to consumer electronics. The result was a device that transformed people's relationship with mathematics, making complex calculations accessible anywhere, anytime, just as the AGC had made precise navigation possible far from Earth. The success of the EL-8 and subsequent Japanese calculators demonstrated that the lessons of the AGC could be applied profitably to consumer products. This encouraged Japanese manufacturers to explore other applications of miniaturized computing, from digital watches to portable music players, from car engine controllers to video game consoles. The AGC's influence extended beyond the technical realm into how Japanese companies organized their engineering teams. Margaret Hamilton's software team at MIT had pioneered new approaches to system reliability and error handling that required close collaboration between hardware and software engineers. Japanese electronics manufacturers, traditionally organized in rigid departmental structures, began experimenting with more integrated development teams. NEC was among the first Japanese companies to adopt this approach, creating cross-functional teams that included both hardware and software engineers working together from the earliest stages of product development. This organizational innovation, inspired in part by studying how the AGC had been developed, contributed to NEC's rise as a global technology leader in the 1970s and 1980s. The AGC's impact was particularly profound in Japan's nascent aerospace industry. Although Japan's space program was modest compared to those of the US and USSR, it was growing in ambition. Engineers at the National Space Development Agency of Japan, NASDA, now part of JAXA, studied the AGC intensively as they developed guidance systems for Japanese rockets and satellites. Hideo Itokawa, often called the father of Japanese rocketry, arranged for detailed briefings on the AGC for his team. "We must understand not just what the Americans built," he instructed them, but how they thought about the problem. Their approach to integrating systems and managing complexity is what we must learn. This focus on systems integration, understanding how different components work together as a unified whole, would become a defining characteristic of Japanese engineering. Companies like Toyota would later apply similar principles to manufacturing, developing the famous Toyota production system that revolutionized how complex products are made. By the mid-1970s, as Japan's electronics industry gained global prominence, American observers began noting the influence of the Apollo program on Japanese technology. A 1975 report by the U.S. Department of Commerce noted, "Japanese electronics manufacturers have studied NASA's approach to miniaturization and reliability with remarkable thoroughness. Many of their recent innovations show clear evidence of principles first demonstrated in the Apollo guidance computer." The report particularly highlighted how Japanese companies had adopted and improved upon the concept of designing for manufacture that had been crucial to the AGC's development. The MIT team had worked closely with Raytheon, the primary manufacturer of the AGC, to ensure that their complex design could be reliably produced in quantity. Japanese manufacturers took this concept further, developing new approaches to quality control and automated manufacturing that would give them a significant competitive advantage. Japanese engineers who had studied the AGC also noted its remarkable energy efficiency, another necessity of spaceflight that would become increasingly important in consumer electronics. The AGC operated on just 70 watts of power, less than a typical light bulb. This focus on power efficiency would become a defining characteristic of Japanese electronics, from early calculators to the laptop computers that Japanese manufacturers would pioneer in the 1980s. Perhaps the most profound impact of the AGC on Japanese technology came through its influence on semiconductor development. The integrated circuits used in the AGC, while revolutionary for their time, were primitive by later standards, containing just a few transistors each. But they demonstrated the potential of integrated circuit technology at a time when many engineers remained skeptical. Japan's electronics manufacturers, having witnessed the AGC's success, invested heavily in semiconductor research and manufacturing. By the late 1970s, Japanese companies were producing memory chips that rivaled or exceeded American designs in quality and reliability. By the mid-1980s, Japan would briefly overtake the United States as the world's leading producer of semiconductor memory, with companies like Hitachi, NEC, and Toshiba dominating the global market. The development of Japan's semiconductor industry reflected many lessons learned from studying the AGC. Japanese manufacturers placed extraordinary emphasis on reliability, developing manufacturing processes that produced chips with remarkably low defect rates. They focused on memory technologies, recognizing, as the AGC's designers had, that memory constraints were often the limiting factor in computing performance. Dr. Ikeda, whose initial disbelief at the AGC's specifications had given way to admiration, played a key role in Hitachi's semiconductor strategy. The Apollo computer showed us that integrated circuits were the future, he told a gathering of Hitachi engineers in 1976, but it also showed us that reliability could not be sacrificed for performance. This is where Japan's opportunity lies, in building components that combine cutting-edge performance with unmatched reliability. This dual focus on performance and reliability would define Japanese electronics for decades to come. While American companies often prioritized raw performance metrics, Japanese manufacturers typically emphasized consistency, quality, and longevity, values that resonated with consumers and helped build global brands like Sony, Panasonic, and Toshiba. The AGC's impact on Japan's approach to computing was evident in the development of the PC-9800 series by NEC, which dominated Japan's personal computer market in the 1980s. Like the AGC, the PC-98 was designed with specific use cases in mind, rather than as a general-purpose machine. It featured hardware optimized for displaying Japanese characters and was built to extremely high reliability standards. Tomio Goto, who led the PC-98's development team, had studied the AGC's architecture as a young engineer. What I took from the Apollo computer was that success comes not from having the most powerful hardware, he explained in a 1990 interview, but from carefully matching your system to the specific needs of your users. The AGC was designed specifically for lunar navigation, not general computing. Similarly, we designed the PC-98 specifically for Japanese business users, not as a universal machine. This philosophy of purpose-built computing stood in contrast to the more generalized approach of American personal computers like the IBM PC. While the American market standardized around general-purpose machines and software, Japan's computer industry maintained a stronger focus on specialized systems optimized for specific tasks, a difference in philosophy that could be traced back to the influence of the AGC. The AGC's legacy in Japan extended into the 1990s and beyond, influencing developments in mobile computing, robotics, and embedded systems. The constraints that had shaped the AGC's design, limited memory, processing power, and energy, became relevant again as computing moved beyond desktops to smaller, portable devices. Japanese manufacturers, drawing on their institutional memory of the AGC, were well positioned for this transition. Companies like Sony and Toshiba, which had internalized the lessons of doing more with less, became leaders in miniaturized computing devices like laptops and handheld electronics. The PlayStation, Sony's groundbreaking game console, released in 1994, reflected many principles first demonstrated by the AGC. Like the Apollo computer, the PlayStation was a purpose-built system designed to perform specific functions with carefully optimized hardware and software. Ken Kutaragi, the father of the PlayStation, had studied computer architecture at university in the 1970s, when the AGC was a frequent case study. In gaming, as in space exploration, the challenge is to create the illusion of a vast, interactive world using limited computing resources, Kutaragi explained in his book about the PlayStation's development. The Apollo engineers had solved a similar problem decades earlier, creating a computer that could navigate through space with just kilobytes of memory. We approached the PlayStation with the same mindset. The PlayStation's dedicated graphics processing hardware, optimized memory system, and carefully designed programming interfaces all reflected principles first demonstrated by the AGC. While vastly more powerful than the Apollo computer, the PlayStation shared its focused design philosophy, doing one thing extremely well rather than attempting to be a general-purpose computer. This approach proved extraordinarily successful. The PlayStation and its successors would sell hundreds of millions of units worldwide, establishing Sony as a dominant force in the gaming industry. The success validated the approach to computing that Japanese engineers had learned in part from studying the AGC, specialized systems optimized for specific applications rather than general-purpose machines. The AGC's influence also extended to Japan's automotive industry, particularly as cars became increasingly computerized in the 1980s and 1990s. Toyota, Honda, and Nissan all developed sophisticated engine control units, ECUs, that shared the AGC's emphasis on reliability and real-time performance. These systems needed to make complex calculations in milliseconds while operating in harsh conditions, requirements remarkably similar to those that had shaped the AGC's design. Shoichiro Toyoda, who led Toyota's transition to computerized engine management, was known to keep a technical manual about the AGC in his office. "The principle is the same," he reportedly told his engineering team. "Whether guiding a spacecraft to the moon or optimizing fuel injection in an engine, what matters is absolute reliability and precision." Toyota's approach to automotive computing reflected many lessons learned from the AGC. Like the Apollo computer, Toyota's engine control units were designed to operate reliably in extreme conditions, from the freezing temperatures of Hokkaido winters to the scorching heat of desert highways. They incorporated redundant systems and sophisticated error-handling routines that could maintain essential functions even when parts of the system failed, a direct parallel to the AGC's design philosophy. This emphasis on reliability gave Japanese automakers a significant competitive advantage as cars became increasingly dependent on electronic controls. While American and European manufacturers sometimes struggled with electronic reliability issues, Japanese cars developed a reputation for consistent, trouble-free operation, a reputation built in part on computing principles first demonstrated by the AGC. As the 21st century approached, a new generation of Japanese engineers began revisiting the AGC with fresh eyes. The constraints that had shaped the Apollo computer, limited memory, processing power, and energy, were becoming relevant again as computing moved beyond desktops to smaller, portable devices like mobile phones and digital assistants. In 1997, a team at Tokyo University, led by Professor Yoshihiro Kusumoto, began a project to create a complete simulation of the AGC, preserving its architecture for future study. The Apollo Guidance Computer represents a unique moment in computing history, Kusumoto explained. It was developed with constraints that forced innovation in ways that still have relevance today. As we move into the era of ubiquitous computing, with small devices embedded in everything around us, the AGC's lessons become valuable again. The project attracted significant attention from Japan's technology industry. Engineers from companies like Sony, Hitachi, and Fujitsu volunteered their time, many of them inspired by the stories they had heard throughout their careers about the legendary American computer that had guided astronauts to the moon. One of those volunteers was Yutaka Matsuoka, who would later lead Sony's robotics division. "Working on the AGC simulation changed how I thought about embedded systems," he recalled. The Apollo engineers had created a computer that was not just technically sophisticated, but also deeply human-centered. It was designed to work with astronauts under extreme pressure, to be understandable and predictable, even in crisis situations. This human-machine interface philosophy profoundly influenced my approach to robotics. This human-centered approach to technology became increasingly central to Japanese design philosophy in the digital age. As consumer electronics became more sophisticated, Japanese manufacturers focused not just on technical specifications, but on creating devices that felt intuitive and responsive. This emphasis on the human experience of technology could be traced back to the AGC, which had pioneered the concept of computers as partners rather than just tools. The AGC's influence was evident in Japan's approach to mobile phones in the early 2000s. While American and European manufacturers focused primarily on voice communication, Japanese companies created phones with multiple functions integrated into a single device. This concept of a multifunction device with a simple interface echoed the AGC's design philosophy, where a single computer handled navigation, guidance, and control through an interface simple enough for astronauts to use while wearing gloves. Japanese mobile phones of this era were marvels of miniaturization and integration, packing cameras, music players, email clients, and web browsers into pocket-sized devices years before smartphones became common in Western markets. This approach, combining multiple functions in a single, carefully designed device, reflected the integrated system design philosophy that Japanese engineers had studied in the AGC. The release of the iPhone in 2007 represented a moment of reckoning for Japan's electronics industry. Apple's revolutionary smartphone embodied many principles that Japanese engineers had studied in the AGC: elegant integration of hardware and software, a focus on the user experience, and doing more with limited resources. Yet it was an American company, not a Japanese one, that had created this groundbreaking device. This sparked soul-searching within Japan's technology sector. Masayoshi Son, the founder of SoftBank, was among those who recognized that Japan had lost some of the innovative spirit that had characterized its rise in the 1970s and 1980s. "We became too comfortable with incremental improvements," he said in a 2010 speech. "We forgot the lesson of the Apollo program, that sometimes you need to set seemingly impossible goals to achieve breakthrough innovation." Son's perspective reflected a growing recognition within Japan that the country needed to recapture the sense of bold ambition that had driven its earlier technological advances. The Apollo program, and the AGC in particular, became a reference point in discussions about revitalizing Japan's innovation ecosystem. In 2012, as part of an effort to inspire a new generation of Japanese engineers, JAXA, Japan Aerospace Exploration Agency, organized a special exhibition about the Apollo guidance computer. The exhibition featured original AGC hardware on loan from the Smithsonian, alongside displays explaining its significance to Japan's technology development. At the opening ceremony, Dr. Mamoru Mori, Japan's first astronaut and then the director of Japan's National Museum of Emerging Science and Innovation, reflected on the AGC's enduring legacy. What made the Apollo guidance computer special was not just what it did, but what it represented, he said. It showed that with clear purpose, creative thinking, and meticulous execution, we can solve problems that seem beyond our reach. This is a lesson that remains as relevant today as it was half a century ago. The exhibition proved unexpectedly popular, attracting not just technology enthusiasts, but families with children. Many Japanese parents, themselves engineers or scientists, wanted their children to understand this pivotal moment in technological history. The AGC had become more than just a historical artifact. It was a symbol of human ingenuity and determination. For many young visitors, the most surprising aspect of the exhibition was the AGC's limited capabilities compared to the smartphones they carried in their pockets. The fact that humans had reached the moon with computing power less sophisticated than a modern digital watch was almost incomprehensible to a generation that had grown up with ubiquitous computing. This contrast became a powerful teaching tool. Exhibition guides used it to explain how creative thinking and elegant design could overcome seemingly insurmountable technical limitations, a lesson as relevant to 21st century challenges as it had been to the moon landing. The AGC became a touchstone for discussions about innovation, demonstrating how breakthrough achievements often come not from raw computing power, but from innovative approaches to using available resources. As interest in the AGC revived, Japanese researchers began uncovering new details about how it had influenced Japan's technology development. Historians at the Tokyo University of Technology conducted interviews with retired engineers who had been active during the 1960s and 1970s, documenting their recollections of how knowledge about the AGC had spread through Japan's technical community. These interviews revealed a more complex story than had previously been understood. While official technical exchanges between American and Japanese engineers had been limited, information had flowed through various informal channels. Japanese engineers working for international companies Academic researchers attending conferences and technical publications had all played roles in transmitting knowledge about the AGC to Japan. Perhaps most surprisingly, the interviews revealed that several Japanese engineers had worked directly on the Apollo program through MIT's international research collaborations. These individuals, who had returned to Japan and taken positions in companies like Hitachi and NEC, had brought first-hand knowledge of the AGC's development process. Their influence, while rarely acknowledged in official histories, had been significant in shaping Japan's approach to computer development. One such engineer was Takeo Kanade, who had worked at the MIT AI lab in the late 1960s before returning to Japan and eventually becoming a pioneer in computer vision technology. "What I learned at MIT wasn't just technical knowledge," Kanade explained in a 2015 interview. "It was a way of approaching problems, of breaking down seemingly impossible challenges into manageable parts." This was the true legacy of projects like the Apollo Guidance Computer. The rediscovery of these connections between the Apollo program and Japan's technology development coincided with renewed interest in space exploration globally. As both established space powers and new entrants announced ambitious plans for lunar and Mars missions, the achievements of the Apollo program took on new relevance. Japan's own space program had grown significantly since the days when Japanese engineers had first studied the AGC. JAXA was now developing sophisticated spacecraft for lunar and planetary exploration, including the Hayabusa series of asteroid sample return missions. These spacecraft incorporated guidance computers that, while vastly more powerful than the AGC, still followed many of the design principles pioneered by the Apollo program. In 2019, as the world celebrated the 50th anniversary of the Apollo 11 moon landing, Japanese technology companies reflected on the AGC's continuing influence on their work. At Fujitsu's research laboratory in Kawasaki, engineers demonstrated how principles first established in the AGC informed their current work on autonomous systems and artificial intelligence. "The fundamental challenge remains the same," explained Dr. Seishi Takamura, a Fujitsu research fellow. "How do you create systems that can make reliable decisions with limited information in unpredictable environments?" The Apollo Guidance Computer was perhaps the first computer entrusted with truly life-critical decisions in such an environment. The approaches developed then, redundancy, fault tolerance, prioritization of critical functions, remain central to our work today. This continuity of principles across generations of technology development highlighted the AGC's enduring significance. While the specific technologies had evolved dramatically, from integrated circuits with a few transistors to modern microprocessors with billions, the core engineering challenges remained remarkably similar. For Japan's technology industry, facing intense competition from both established American companies and rising Chinese manufacturers, the story of the AGC offered both inspiration and caution. It demonstrated how focused innovation could achieve seemingly impossible goals, but also how technological leadership could shift between nations. Akio Toyoda, the president of Toyota and grandson of the company's founder, referenced this dual lesson in a 2020 speech about the company's investments in autonomous vehicles and robotics. Half a century ago, American engineers created a computer that could guide spacecraft to the moon when computing was in its infancy, he noted. Today, as we enter the age of artificial intelligence and autonomous systems, we must show the same courage and creativity. Leadership in technology is never permanent. It must be earned through continuous innovation. This sentiment that technological leadership requires constant renewal reflected Japan's experience in the decades since the Apollo program. The country that had once watched in amazement as American computers guided spacecraft to the moon had itself become a global technology leader, only to face new challenges as computing continued to evolve. The cyclical nature of technological leadership was particularly evident in the semiconductor industry. Japanese companies that had once dominated memory chip production found themselves challenged by South Korean and Taiwanese manufacturers who had studied and improved upon Japanese manufacturing techniques, just as Japanese engineers had once studied American aerospace technology. This pattern of technological knowledge flowing across national boundaries, from the United States to Japan, from Japan to other Asian nations, and increasingly back to the United States through global innovation networks, demonstrated how the AGC's legacy had transcended its American origins to become part of a global technological heritage. In 2023, as both NASA and JAXA announced new plans for lunar exploration, engineers from both countries gathered at a symposium in Tokyo to discuss the legacy of the Apollo guidance computer and its relevance to modern space missions. Despite the enormous advances in computing power since the 1960s, many of the fundamental challenges remained the same. How to ensure reliability in the harsh environment of space, how to manage limited resources, and how to design systems that could operate autonomously when communication with Earth was impossible. Dr. Shinji Mitsuya, a JAXA engineer working on guidance systems for Japan's planned lunar missions, summarized the AGC's enduring legacy. The genius of the Apollo guidance computer wasn't in its raw specifications, which by today's standards are incredibly modest. It was in how those limited resources were utilized to achieve something extraordinary. As we develop the next generation of spacecraft computers, we continue to be guided by that same principle. It's not about having the most powerful hardware, but about using what you have with intelligence and precision. This perspective, focusing on the efficient use of resources rather than raw power, reflected the lasting influence of the AGC on Japanese engineering philosophy. From consumer electronics to automotive systems, from industrial robots to space technology, the lesson that elegant design could overcome hardware limitations had shaped Japanese innovation for generations. The symposium also explored how the AGC's influence had extended beyond technical considerations to shape corporate cultures and national innovation strategies. The Apollo program had demonstrated the power of setting ambitious goals to drive technological progress, a lesson that had influenced Japan's approach to industrial policy in the 1970s and 1980s, and was now being rediscovered as the country faced new technological challenges. The Apollo guidance computer wasn't just a technical achievement. It was the product of an innovation ecosystem that brought together government, academia, and industry in pursuit of an audacious goal, noted Dr. Relja. Hiroshi Amano, winner of the Nobel Prize in Physics for his work on blue LEDs. This model of collaborative innovation remains as valuable today as it was in the 1960s. Perhaps even more so as we face global challenges that require unprecedented technological solutions. As Japan and the United States renewed their collaboration in space exploration through programs like the Artemis lunar missions, the story of the Apollo guidance computer served as a reminder of how technological exchange between nations could drive innovation forward. The computer that had once stunned Japanese engineers had ultimately inspired them to achievements that would, in turn, influence American technology. In this cycle of innovation and influence, the true legacy of the Apollo guidance computer could be found not just in the specific technologies it pioneered, but in how it demonstrated humanity's capacity to overcome seemingly insurmountable challenges through creativity, determination, and collaboration across borders and cultures. The story of the AGC's influence on Japanese technology offers a powerful reminder that innovation is rarely a linear process contained within national boundaries. Rather, it flows across borders and generations, with each breakthrough building on what came before and inspiring what will follow. The computer that guided humans to the moon has, in this way, helped guide humanity's technological journey for more than half a century, a journey that continues today in laboratories and workshops around the world, where engineers still draw inspiration from the remarkable device that first showed what computers could achieve.